Welcome to Momentum in Motion, the podcast where we explore one of physics's most fundamental principles. I'm Priya, and today we're diving deep into the conservation of momentum, a concept that governs everything from car crashes to billiard balls colliding on a pool table.
And I'm Marcus. Priya, before we jump into the experiments, can you explain what momentum actually is? I know it's related to motion, but there's more to it than that, right?
Absolutely. Momentum is the product of an object's mass and its velocity. We express it as P equals mv, where P is momentum, m is mass, and v is velocity. Think of it as the oomph an object has when it's moving. A bowling ball rolling slowly has significant momentum because of its mass, while a tennis ball moving fast also has momentum because of its velocity.
That makes sense. So if momentum is conserved, what does that mean exactly?
Great question. The law of conservation of momentum states that in a closed system, one where no external forces act, the total momentum before an interaction equals the total momentum after the interaction. This holds true whether objects are colliding, exploding, or separating. It's one of nature's most reliable rules.
Let's talk about real-world examples. What happens when two cars collide?
Perfect example. Imagine a car with mass 1,000 kilograms traveling at 10 meters per second collides with a stationary car of equal mass. Before collision, the total momentum is 1,000 times 10 equals 10,000 kilogram meters per second. After collision, if they stick together, they move as one unit with combined mass 2,000 kilograms. Using conservation of momentum, we can calculate their final velocity. 10,000 equals 2,000 times v final, so v final equals 5 meters per second. The momentum is conserved, but distributed differently.
Interesting. But I've heard there are different types of collisions. What's the difference?
Excellent observation. There are two main types, elastic and inelastic collisions. In elastic collisions, both momentum and kinetic energy are conserved. Objects bounce off each other without sticking. Think of billiard balls or atoms colliding. In inelastic collisions, momentum is conserved, but kinetic energy is not. Some energy converts to heat, sound, or deformation. Car crashes are typically inelastic.
Now, you mentioned experimental data. Tell us about the collision studies you've analyzed.
We examined several collision experiments using dynamics carts on a frictionless track. In one scenario, cart 1 with mass 8.2 kilograms moving at 0.217 meters per second collided with a stationary cart 2. Before collision, total momentum was 0.82 times 0.217 equals 0.178 kilogram meters per second. After collision, cart 1 moved at 0.109 meters per second and cart 2 at 0.089 meters per second. The total momentum afterward was 0.82 times 0.109 plus 0.82 times 0.089 equals 0.162 kilogram meters per second. The slight difference reflects experimental measurement uncertainty.
What about when the masses were unequal?
That's where it gets really interesting. In an unequal mass collision, cart 1 had mass 0.62 kilograms, moving at 0.319 meters per second, while cart 2 was stationary. Initial momentum was 0.62 times 0.319 equals 0.198 kilogram meters per second. After collision, cart 1 moved at 0.109 meters per second and cart 2 at 0.099 meters per second. The final momentum was 0.62 times 0.109 plus 0.41 times 0.099 equals 0.108 kilogram meters per second. Again, momentum was conserved with an experimental error.
What about the kinetic energy in these collisions?
Excellent question. Kinetic energy is calculated as Ke equals half mv squared. In the first collision, initial kinetic energy was half times 0.82 times 0.217 squared equals 0.019 joules. After collision, the total kinetic energy was half times 0.82 times 0.109 squared plus half times 0.82 times 0.089 squared equals 0.0065 joules. Notice the kinetic energy decreased significantly. This indicates an inelastic collision where energy was lost to deformation, sound, and heat.
So momentum is always conserved, but energy isn't necessarily.
Precisely. That's the key distinction. Momentum is always conserved in isolated systems. Energy, however, can transform between kinetic, potential, thermal, and other forms. In inelastic collisions, kinetic energy converts to other forms. This is why momentum conservation is so powerful. It's a universal principle that applies to all collisions.
How do scientists use this principle beyond laboratory experiments?
Conservation of momentum has countless applications. Engineers use it to design safer vehicles by analyzing crash dynamics. Astronomers apply it to understand celestial collisions and explosions. Particle physicists rely on it to detect new particles and accelerators. Even forensic scientists use momentum conservation to reconstruct accident scenes and determine vehicle speeds before impact.
That's fascinating. What's the most important takeaway for our listeners?
Remember that conservation of momentum is a fundamental law of nature. In any isolated system, the total momentum before an event equals the total momentum after. Whether you're analyzing collisions, explosions, or everyday interactions, this principle holds true. It's a powerful tool for understanding and predicting motion in our universe.
Thanks, Priya. This has been incredibly enlightening. For our university-level listeners, momentum conservation connects classical mechanics to modern physics and remains essential across all scientific disciplines.
Thank you, Marcus. Thanks to everyone listening to Momentum in Motion. Keep exploring the physics that shapes our world.